To begin with, we need to understand what a hash table is. A hash table is a concrete implementation of an abstract data type known as an associative array. It uses a hash function to map a key to a given value. In a normal array, we can use integers to store and retrieve values. In an associative array, we can use an alternative type of key, such as a string, to do the same thing. Here is an example of what a hash table looks like. We can see we have names, which are strings, on the left-hand side. We will be using these as keys. These names will be passed through a hash function, which will output a valid index inside of the array where we can store a value associated with that key. So what is a hash function? A hash function takes an input and outputs an integer. We can use hash functions to map keys to a given integer index inside of an array. Hash functions are deterministic, meaning the same inputs will always produce the same exact output. An example of extremely simple hash function would be a function that takes a string as an input, such as Bob, and then calculates the sum of all of the ASCII values of each character. So in this case, we can split the input string out into each character, identify their ASCII values using this ASCII table over here, and then calculate their sum. Lastly, since we want to produce an index in an array, we want to modulo that sum with the length of the array so we produce a valid index that is in bounds.
Under the hood, a hash table will use an internal array for storage. Data will be stored in that internal array as a struct with a key and a value. The key is going to be a string that we hash to find the index, and the value is the data to be stored at that location. Collisions occur when two keys correspond to the same index after hashing. Our example hash function is getting the total sum of each character's ASCII value. With that hash function, we will run into a collision if we insert the keys Andrea and Adrian. Andrea and Adrian have the same characters, and so the total ASCII value is the same as well. Therefore, these keys will collide when converted into an index. Even beyond our example hash function, collisions will occur with real-world hash functions too. Because of these collisions, we need some kind of strategy to resolve the collisions and still be able to find the values.
What is collision resolution in hash tables? Collision resolution strategies define how the tables store and retrieve colliding elements. There are two general purpose strategies for handling collisions, which are closed addressing, also known as separate chaining, and open addressing. With closed addressing, each table index stores a collection, which is usually a linked list or vector of elements that hash to the same value. When a collision occurs in closed addressing, the new key is appended to the index that the collision happened. For example, if we are inserting A into the list and the hash is equal to index 0, it'll just be appended to index 0. If D also is equal to index 0, it'll also be appended to index 0. One key trait of the table is that it never completely fills. The elements just spill over into external structures. With open addressing, all elements are stored directly inside the hash table. When a collision occurs in open addressing, the algorithm probes other indices according to a deterministic rule. For example, we have A at index 0 of the table. If we wanted to insert AA, it would normally go at index 0, but that index is full. So we'll check index 1, which is also full, index 2, index 3, and then we'll eventually insert into index 4, where there are no elements there. A key trait is that there are no external data structures. All the collisions are resolved by relocation within the table. Some common probing strategies are linear probing, quadratic probing, and double hashing.
Cuckoo hashing is a form of open addressing that provides fast and predictable lookup times. It uses two additional strategies, multiple choice hashing and relocation hashing. Multiple choice hashing utilizes two internal arrays or tables to store the elements. In Cuckoo hashing, any given element has two possible valid placements, being in one of two of these arrays. Each of these arrays has a unique hashing function associated with them to calculate a placement for the new element. Relocation hashing is the process of resolving collisions by moving an existing element into a new location. And cuckoo hashing, when a collision occurs, the new element being inserted kicks out the element that's currently occupying the spot and takes its place. The displaced element is then relocated to its alternate location. This process can repeat until an empty spot is found or a rehash is required. The cuckoo hashing algorithm gets its name from the real-life behavior of cuckoo birds, which push their siblings or other eggs out of the nest when they hatch. And that's modeled in our algorithm when a new element evicts an older one.
Let's take a look at how the insert operation actually works to help us better understand how collisions are resolved. Say we want to insert a new element into our hash table. This element will be A. The first step is to calculate one of the placement options for A. In this case, we'll use the first hash function, which is associated with the first table. This hash function will output a hash code of 2, which points to a cell in table 1 that is already occupied. Because this cell is occupied, we need to check the alternative placement for A. This time, we'll use the second hash function, which is associated with the table 2, and we'll calculate an index where A could be in that second table. We can see here that the hash code will point us to an empty cell, meaning we found a valid placement for A. It is possible, however, that both of the placement options for A will be occupied. You can see what that would look like in this drawing right here. If both of the placement options for A are occupied, we will perform an eviction process. We will push the older element out of its cell, replacing it with the newer one, but then we'll need to find a new placement for the older element. The first thing we'll do is check the alternative placement option for the older element. We can see here this results in a hash code of 2 in table 1, which points to a cell that's also occupied. We will continue this process of eviction, removing the older element from the table and replacing it with the newer to be inserted element until either we find a valid placement for every element in the table or one of two conditions are met. The first of which being that we detect a cycle in evictions. This occurs when you evict the same element more than once. The second condition being we've met a certain threshold of evictions and we cannot evict any more elements. If either of these conditions are met, we will have to rehash the table. When you rehash the table, you will pick two new hash functions and you'll reinsert every element in the data structure. Hopefully this will result in a valid placement for every single element, but it is possible that multiple rehashes will need to occur before we find a spot to put every element in our data structure.
Let's say we want to search our hash table for the value that corresponds to our key. The first step would be to apply the first hash function associated with table 1 to our key, x, which will input the index value which we want to search in. In the case that the value at that index matches our key, we will simply return the value. If we do not find the key at its associated index in table 1, we will apply the hash function associated with table 2 to the key, and we'll check the corresponding location in the second table. If our key isn't located in either of our hash tables, we will return null. We know for a fact that the key is either in one of two locations in the hash table or that it doesn't exist at all. In the case that we want to delete a value from our hash table, we'll go through the same steps as in the search function. However, in this case, if we find the element in either table, we'll simply wipe that index. If we don't find the element in either table, no deletion will occur.
Here is the pseudocode that would be responsible for the previous examples. We won't get into the specifics, but feel free to pause and examine the code more closely. The lookup function takes in a struct with a key and a value, then returns either the value stored in the array for the key or returns null if the key is not found in the hash table. The delete function takes in the same struct with a key and a value and will effectively remove the value that corresponds to the key. The insert function once again takes in the same struct and will insert the value at the index that corresponds to the key.
In terms of time complexity, the search operation in cuckoo hashing runs in a constant time being O of 1. That's because each key can only exist in one of two possible locations. If the value is not found in the first position, it has to be in the second position, so only 2 checks are ever needed. When we're deleting, the operation also runs in O of 1 time, since the key we want to delete can only be located in one of 2 possible positions. The algorithm can find and remove it in a constant time. For the insert operation, our worst case scenario runtime is going to be O of n. And this happens when a rehash occurs and every element in the table needs to be reinserted. But rehashing happens very rarely, which is why the amortized runtime for insertion is still considered O of 1. However, it is important to be aware of the worst case behavior. As a key value data structure, a hash map is very useful so we can quickly access, modify, or relate data elements. The applications of Cuckoo hashing range from software development all the way to databases and even routers because of its O of 1 lookup time. It also has efficient runtimes for operations that make Cuckoo hashing an extremely useful tool.
Yeah!